Okay, so we just looked at 10.5 absolute convergence. So here we have a couple of definitions. But the most important thing in the last video was this ratio test. So we have a series, and we take the limit of consecutive sequence terms of the absolute value as n goes to infinity. If that approaches a number, if that number is less than 1, it converges absolutely. If that number is bigger than 1, then it diverges. If that number is equal to 1, then the test is inconclusive. So we're going to look at a few different examples here. The first example we're going to look at is this thing. So we're going to have an infinite series as n goes from 0 to infinity of 2 to the n plus 5 all divided by 3 to the n. Okay, so remember that we have a bunch of different tests so far. We have the nth term test. The nth term test is going to tell us nothing because this sequence does converge to 0, so that test is inconclusive. You could try to integrate this, but integrating this is very, very difficult. You could also probably just do a geometric series here and look at the addition of two different terms. That would be dividing the 3 to the n by both of these terms up top, and you would have two different geometric series, and then you could use that sum theorem that we've looked at before and then add the two values together. But let's use the ratio test just to get some practice. So if we want to use the ratio test, remember we're going to be looking at that limit. So this is going to be the limit as n goes to infinity of, this is just writing it out generically for now. We're looking at the n plus 1 term, and we're going to divide that by the nth term. So let's actually write out what the n plus 1 term and the nth term are going to come out to be. So I'm going to just kind of drop the limit for now because I don't feel like writing it over and over and over again. This is going to be the absolute value of, and it's going to be a very, very complex fraction here. So bear with me as I write this all out. I practiced before I started the video. So here we go. 2 dollars. So now we're plugging in n plus 1 into my sequence terms here. Basically just replacing my n's with n plus 1. So 2 to the n plus 1 plus 5 all divided by 3 to the n plus 1. So that's my n plus 1 term, and I'm going to divide that by just the nth term. That's just copying the sequence as is here. So 2 to the n plus 5 all divided by 3 to the n. And just to close off the absolute value here. Awesome. All right, cool. So we need to simplify this down. We're looking at the absolute value of the n plus 1 term divided by the nth term. And we're going to use a couple of tricks here. First things first is that we have this complex fraction. You want to think of it like the top fraction multiplied by the reciprocal of the bottom fraction. So I don't really want to write that out. I hope you guys write this out on your own just to make sure that this is really what's going to happen. So what's going to happen is you're going to have a 3 to the n that's going to come up to the numerator, and it's going to be divided by this 3 to the n plus 1. So 3 to the n is going to cancel out, and you're just going to have a 1/3 left over. Now for the other part, there's not really much that's going to happen here. Unfortunately, you're just going to be left with this, the rest of this fraction. So we're still going to have that 2 to the n plus 1 in the numerator, and then we're going to have the plus 5. In the denominator, we're going to have the 2 to the n plus 5. Okay, great. Now, the next trick that you want to do is you just want to kind of look at what this is going to approach. And to find what this is going to approach, what we're going to do is we're going to divide everything by this 2 to the n. All right, so we're going to leave the 1/3 out in front. That's just multiplied on, so that's not going to change anything. But when you divide the top by 2 to the n, we're just going to have a 2 left over. Plus, we're going to have this 5 divided by 2 to the n. In the denominator, I'm going to divide 2 to the n by 2 to the n, which is 1. And then plus this 5, again, is going to be divided by a 2 to the n. Don't forget that we're eventually taking the limit as n goes to infinity, so maybe now you can see what this is going to approach. Right. So, up top here, we're just going to take the limit. Sorry if that made a loud noise for you. We're going to take this previous thing as it goes to infinity. So this is going to approach. We're going to have that 1/3 out in front. And then this complex fraction here, if 2 to the n is going to infinity, this just goes to 0, this term just goes to 0, so this approaches 2 times this 1/3, which is going to give us 2/3. Okay, so don't forget that what that tells us is that our p is going to be equal to this 2/3, where this p is this limit. Our number came out to be less than 1, and then by the ratio test up above here, if this number comes out to be less than 1, that says that thus the series, it doesn't just converge, it converges absolutely. Now I know that doesn't really mean much for this series, because this series is already only positive numbers, but if there were negative terms here, this would be a little bit more powerful of a statement. Alright, let's look at one more example. Alright, so my next example is going to be this one. So now we're going to look at the series. I'm just going to write it as the sequence, though, for now. So the sequence values, but eventually the series of 2n factorial divided by n factorial n factorial. Alright, and then the question is going to be, does the series converge of a sub n? Okay. We've looked at some factorials before. I hope you guys remember what a factorial is. So if we're looking at this as a series, the ratio test is always going to be what you want to use when you have these factorials. The ratio test works very well with the factorials. So we're going to do the same thing that we were doing before using the ratio test. We want to look at the limit as n goes to infinity of the ratio of the n plus 1 term with the nth term. Alright, so let's write this all out. So we're going to do the absolute value, and we're just going to plug n plus 1 in for all of these n's. And you have to be very careful when you're plugging it into these factorials. I'll go ahead and get a fraction started here. So if I plug n plus 1 into this, then my numerator is going to be 2 times n plus 1 all factorial. So make sure that you're putting that n plus 1 in its own parentheses like that, because you are going to have to distribute the 2 in there. And then my denominator is going to be n plus 1 factorial times n plus 1 factorial. Alright, the denominator, here just my sequence term a sub n, is just going to be copying this down. So it's another fraction, and we're going to have 2n factorial, and then divided by just n factorial, n factorial. Okay. This looks awful, and I know it looks awful, but we can use some of the tricks that we have with factorials to simplify this down. So what I'm going to do is I'm going to rewrite this as the top fraction divided by the bottom fraction, and I have the luxury of just copy pasting. So there's my numerator fraction, and this is going to be divided by, how do you put a division symbol in there? There's got to be an easy way. There it is. So we're just going to divide that by the denominator. Okay, but of course, writing it out like this, whenever you're dividing fractions, is the same thing as multiplying by the reciprocal. So just imagine that this thing is flipped up. So if I do flip that up, now what I'm going to do is I'm going to rewrite some of these terms. This I'm just going to leave as is. It's this first fraction that I'm going to rewrite using the definition of factorials. Also, don't forget that this 2 should really be distributed into this parentheses here. So I'm just going to cheat a little bit and write down what this would be. This would be 2n plus 2 up top when you just multiply the 2n and all that. Okay. So it's still an absolute value. You could drop that if you really wanted to, because it's not doing anything for us anymore. But this first fraction here, 2n plus 2 factorial, is the same thing as 2n plus 2 times 2n plus 1 times 2n factorial. Now that factorial is only on the 2n part. So make sure that makes sense to you. It's just using the definition of factorial where you multiply by that term, then the next term down, the next term down, the next term down, all the way down to 1. So 2n plus 2 factorial is 2n plus 2 times the next number down, 2n plus 1, times the next number down, 2n. Same thing I'm going to do here. N plus 1 factorial is the same thing as n plus 1 times n factorial. And then my other n plus 1 factorial will do the same thing. N plus 1 times n factorial. Okay. Now this is still going to be divided by this, but now I'm going to rewrite that a little bit as multiplied by the reciprocal n factorial divided by that 2n factorial. Okay. I know this looks awful, and I hope you guys are writing this on your own notes. You can kind of visualize a little bit better what's going on here, but a lot of stuff is going to cancel out. This 2n factorial in the numerator cancels out with this 2n factorial. This n factorial cancels out with this n factorial. This n factorial cancels out with this one. So all we're going to have left, I'm going to go ahead and drop the absolute values now, is another fraction where we have the 2n plus 2 on top, the 2n plus 1 on top, and then in the denominator, we're going to have an n plus 1 times another n plus 1. You could write that as n plus 1 squared if you really wanted to. Okay, but that is all that is left over here. Now, don't forget that we're still taking the limit as n goes to infinity of this term that we have at the bottom here. And this is something that we've seen before. You're technically using L'Hopital's rule here, but I'm just going to kind of cheat a little bit. So just to simplify this down a little bit, this is similar to the ratio of 4n squared divided by n squared. So you're just looking at the leading terms of the numerator. If you were to multiply all this out, you would have a 4n squared out in front. If you were to multiply the denominator out, you would have an n squared out in front. And then that, remember, approaches the horizontal asymptote. So this is just going to approach 4. Don't forget that this is my p-value. So thus, p is equal to 4 from the ratio test. So if I go back up to the rules for the ratio test, my number p came out to be 4, which is bigger than 1. That tells me that this series up top diverges.